Welcome to the Deep Dive, the show where we grab the latest cutting-edge research, distill it down, and deliver those absolute must-know insights straight to your brain. Today, we're plunging into a truly fascinating challenge in the world of large language models. You might think it's all about just throwing more and more data at them, right? Billions of tokens, ever-growing data sets. But what if the core problem isn't just more data, but finding the right data? The truth is, our current methods for picking quality data often rely on, well, a lot of intuition. And honestly, quality itself can be a pretty slippery concept.
It absolutely can be, yeah. And that's exactly what this groundbreaking paper unpacks. It tackles the fundamental challenge of selecting the most impactful pre-training data for LLMs. What's truly novel here is an approach called benchmark targeted ranking, or BETR. Instead of these, vague ideas of quality, BTR explicitly aligns pre-training documents with the very evaluation benchmarks we use to test these models.
And the results, well, they are genuinely eye-opening, and this is where it gets really exciting for anyone working with or curious about LLMs. Okay, so for a quick snapshot, this deep dive unpacks a groundbreaking paper tackling a core challenge in LLM training, selecting the right pre-training data. The method, BTR, explicitly aligns pre-training documents with evaluation benchmarks, moving beyond just gut feelings about quality. And the results are pretty striking. BTR gets a 2.1x compute multiplier over a strong baseline and a massive 4.7x multiplier over just using unfiltered data. Think about that. It's like discovering a secret ingredient that lets you train your AI models almost 5 times more efficiently. That's huge. It's not just a small tweak. It's a potential shift that could dramatically lower costs and speed up research. Plus, it consistently improved performance on 9 out of 10 tasks across all model sizes, and it even generalized well when targeting benchmarks different from the ones it was evaluated on.
And a really crucial finding from this work is the clear scaling trend it reveals. Larger models, it turns out, actually require less aggressive data filtering, while smaller models benefit immensely from highly targeted data. So optimal data selection isn't, one size fits all. Overall, this research really highlights that directly matching pre-training data to target tasks precisely shapes what the model can do. And it shows us that our selection strategies really have to adapt to the model's scale.
So our mission for this deep dive is to pull back the curtain on how BTR actually works, what kind of incredible performance boosts it delivers, and maybe most importantly, why this changes things, how we pick data, design tests, and ultimately build the next generation of LLMs. Get ready for some serious aha moments from this paper. Let's dive in.
Okay, so we all kind of know that pre-training data fundamentally shapes the capabilities of large language models. For years now, improvements in data have been a key driver in LLM advances. But as we just hinted, current methods for data selection often rely heavily on researcher intuition. It's like, we think this data feels good, let's try it, And that's exactly where the ambiguity of quality truly comes into play. Yeah. The paper points out that documents valuable for one task often differ significantly from those useful for another. This poses a fundamental challenge. How do you objectively compare the quality of, say, a complex mathematical proof versus a moving poem versus a breaking news article? Each is high quality in its own domain, sure, but for what specific purpose? Data selection methods already implicitly iterate based on benchmark performance, meaning researchers try a data set, see how the model does on benchmarks, and then refine it. So the natural, incredibly important question this paper asks is, okay, what happens when we make that optimization explicit and direct?
That idea of making data optimization explicit, that really seems like the core innovation here. So how exactly does BTR pull this off? What are the practical steps researchers would take to make this alignment happen?
It's actually a pretty clever 3-step approach, as the paper outlines. First, you need to create a shared understanding space, a place where both your pre-training documents and your benchmark examples can be compared. For this, BD samples about 10 million documents, which sounds like a lot, but it's less than 0.1% of the total data pool, so really a tiny fraction of place, and converts them into numerical representations, or embeddings. And crucially, they also embed each benchmark example individually. They found this performs best empirically. For this shared understanding space, they employed sophisticated models called BERT-like transformer encoders. You can think of these as powerful language processors that read text and distill its meaning into a unique numerical fingerprint. That allows different pieces of text to be accurately compared. They specifically used Arctic Embed L2.0 for the main results.
Okay, so they're taking all these documents and benchmark examples and mapping them into this shared understanding space using embeddings. Once everything's mapped there, basically translating text into comparable data points, what's the next critical step? How do they actually score these documents for usefulness?
Right. The second step is scoring documents by their similarity to these benchmarks. Now, since each pre-training document is potentially compared against thousands of benchmark examples, figuring out how to aggregate all that info into one score is tricky. Do you reward a document that's super close to just one benchmark example, or one that's kind of close to many? BTR opts for something called max aggregation, which scores documents by their best rank across all benchmark examples. What's truly surprising here, and shown in Figure 3 of the paper, is that even the top-ranked documents only show moderate similarities, like around 0.5 to benchmark examples.
Huh, only 0.5.
Yeah, it highlights just how limited the overlap is between general web text and the very specific data points you find in typical benchmarks. In fact, they mention only documents ranked in the top 0.0002% by some benchmark example actually reach the top 10% of BTR scores overall.
Wow, that's a great insight. It shows that the data we might intuitively think of as high quality might still be pretty different from what's needed for specific benchmark tasks. Okay, so with billions of documents in a typical pre-training corpus, how do they scale this process? Direct comparison sounds computationally brutal.
Exactly. That's step 3, predicting scores for the full data pool. Since direct comparison for billions of documents is prohibitive, yeah, they train a lightweight FastX classifier. This is a very simple, efficient model. It's used here just to predict whether documents are likely in the top 10% or bottom 90% by rank, based on the scores from the sample. And here's another counterintuitive finding from the paper, Figure 8, I think. This simple FastX classifier actually matches or even exceeds much larger, more complex language model-based classifiers in terms of downstream model performance.
Really? Even though its own accuracy is lower?
Yeah, even though its validation accuracy is lower, 75.4% compared to 82.4% for a 302 million parameter LM they tested, it really suggests that raw classification accuracy isn't the only thing that matters, maybe not even the main driver, for how effective a data selection method is.
That's truly insightful. So it's these simple yet effective design choices that really drive BTR success. Using those fine-grained targets, going for the single best match scoring, and then relying on surprisingly simple classifiers. It almost makes you wonder if we sometimes overcomplicate things in AI research. And I noticed they did their integrity checks too, right? Confirming no test set leakage. Targeting train versus test sets showed similar results, and decontamination had minimal impact. They're clearly making sure these impressive gains are legit. Okay, so this sounds incredibly promising in theory, but, the proof is in the pudding, right? Does BTR actually work in practice? The paper describes this extensive experimental setup, training over 500 models, wow, covering a vast spectrum of computational power FLOPs from 1019 up to 1022. What did this massive undertaking actually reveal?
Well, the core results are incredibly compelling. Yeah. When directly optimizing for what they call core tasks, their main set of evaluation benchmarks, BTR target core consistently outperforms all baselines across all compute scales. This is really clear in Figure 1 of the paper. To put some numbers on it for you, on one common large data set, DCLM Refined Web, BTR achieves a 1.8x compute multiplier over a strong baseline, which means it requires only 55% of the compute for the same performance level.
That's significant savings.
Absolutely. And against just using unfiltered data, that jumps to a massive 4.7x multiplier, so needing just 21% of the compute. And on another large data set, the Nematron CC data pool, the gains were even more significant. We're talking a 2.5x multiplier over their DCLM baseline there, requiring only about 40% of the compute. And it even beat their own curated high-quality Nematron CC data subset.
So consistently more efficient across different data pools, that's a huge win for anyone actually training these models.
Definitely. And the improvements hold across individual benchmarks, too. It outperformed baselines on 9 out of 10 core tasks on both data pools they tested. And these gains aren't just for models that are still early in their training. They persist even when models are significantly overtrained. They tested a 7B parameter model trained for 10 times the usual data, the 7B 10x scale, and still saw improvements of 1.7 to 1.8 points over the baselines.
That consistency across benchmarks and scales is incredibly compelling. But beyond pure efficiency, does this precise data targeting also give researchers more strategic control over what the model becomes? Can we, for example, intentionally shape a model into a specialist? Or maybe even prevent it from being too narrow?
Yes, precisely. The paper demonstrates this quite clearly. They show what they call diagonal dominance in Table 2. When they targeted individual benchmarks, The resulting models excelled specifically on those tasks or very similar ones. For instance, targeting ARC Easy, which is a knowledge-based benchmark, improved performance on related knowledge benchmarks like ARC Challenge, PsyQ, and MMLU. Makes sense. But here's the fascinating trade-off. Targeting Winogrand, which is more about language understanding, improved performance on another language task, Lambda. But it actually hurt performance on knowledge benchmarks like MMLU.
Ah, okay. So it pushes the model in one direction, potentially at the expense of others.
Exactly. It clearly highlights how specific targeting can create these specialist models. However, they also found that targeting all the core benchmarks, jointly, the target core setup, effectively balanced performance across all tasks. It avoided those sharp trade-offs.
Okay, so what does this all mean for building models in the real world? Can we truly create generalist models with this approach, or are there hidden trade-offs if we narrow our focus too much?
Well, what's really fascinating here is how the method generalizes when you broaden the targets. They tested targeting 39 diverse non-core benchmarks. These were completely separate, disjoint from their main core evaluation suite. And even then, the models trained on data selected using these diverse targets still yielded strong performance on the held-out core tasks. They matched or even exceeded the baselines.
So targeting different benchmarks still helped on the original ones?
Yes, and the research further showed that targeting these diverse non-core benchmarks actually led to better overall core performance than targeting specific supposedly high-quality domains, like DM mathematics or data sets like OH 2.5 plus ELI 5. Table 3 shows this quite nicely. And Figure 5 confirms this phenomenon. Performance consistently improves as you add more diverse benchmarks to the targeting set, after maybe an initial stagnation when you only have one or two. Diversity seems key.
You know, as you describe that, a thought immediately springs to mind. It sounds almost like Goodhart's law in action. Like, if we get too good at optimizing for a limited set of benchmarks, do those benchmarks stop being reliable indicators of true general capability? What did the paper reveal about that potential pitfall?
That's precisely it. Yeah, it looks like a classic example of Goodhart's law, that principle that says when a measure becomes a target, it ceases to be a good measure. The paper reveals a clear rank reversal in Figure 6. While the Goodhart target core models are indeed the best on the core tasks they were trained for, getting a score of 66.5, they drop significantly in performance, down to third place on the held-out non-core tasks, scoring 44.2. They trail behind the model targeted on non-core tasks and even the baseline.
Wow, okay.
It indicates that when a measure, like the core benchmarks, becomes the explicit target for optimization, it often stops being a reliable proxy for the broader, general capability we originally wanted to represent. The document overlap analysis in Figure 7 further reinforces this. It shows a poor correlation between which documents different targeting strategies select and the final capability profiles of the models. It really suggests there's no convergence to a single universal high-quality data set that works perfectly for everything.
Right. It's like the models get too good at the specific test we give them, but that doesn't necessarily mean they're better overall at everything else. Okay, so what additional insights did this comprehensive scaling analysis reveal? Things about data selection that we can only really see when looking across multiple compute scales.
Yeah, the scaling work is really interesting. One key insight is the uneven benefits across different tasks. While BT yields that impressive 4.7x average compute multiplier over using no filtering at all, the benefits vary substantially across individual benchmarks. Figure 9 and Table 5 show this. For instance, knowledge-intensive tasks like ARC Easy see a massive 10.4x compute multiplier. PIQA gets 9.5x. Huge gains there.
Wow.
But then language understanding tasks like web questions see more modest gains around 2.8x, and Winogrand only 1.8x. This suggests that data selection, this kind of targeted selection, works best when the relevant information is quite concentrated and specific to a task, less so for broader skills maybe.
That makes sense. And what about how the amount of filtering changes with model scale? Does the optimal percentage of data to stay consistent no matter how big our model is?
No, and this is a truly crucial finding, shown clearly in Figure 10. Optimal filtering rates predictably become less strict as model scale increases. For smaller compute budgets, say below 3021 FLOPs, aggressive filtering, keeping only the top 3% of data, is optimal.
Okay, very selective.
Very. But as you move to much higher compute, like around 10 and 22 FLOPs, the optimal rate shifts to keeping the top 10%. And then it shifts again to maybe the top 30% beyond 10 and 23 FLOPs. This progression actually follows a power law. They provide the equations. FOPT C, is proportional to C.25 on one dataset, C.14 on another.
So it's predictable.
It seems to be. And this pattern holds even in single epoch training, which suggests it's not just about giving the model more chances to see the data. It implies an inherent requirement for smaller models to be more selective, maybe because they have less capacity. While larger models can actually extract useful signal from noisier or more diverse data, they can handle more complexity.
So we started this deep dive wondering if more data was truly the only answer, and if quality was just this, vague feeling. What we've seen today with B2R is a truly elegant solution. It proves we can be incredibly precise, achieving those significant 2-3x compute multipliers over strong baselines and gaining potentially unparalleled control over our model's futures, whether we want specialists or generalists.
And this really drives home the point that benchmark optimization, whether you do it explicitly like BTR or implicitly through trial and error, it shapes model capabilities predictably. Achieving broader capabilities, therefore, seems to require targeting benchmarks beyond just the ones commonly used for evaluation. We need to think bigger about our targets. However, the scaling analysis suggests a potential path forward, a reconciliation maybe. As models get larger, perhaps combining that with diverse benchmark targeting and the lighter filtering that larger models prefer, maybe we can resolve that specialization versus generality trade-off and build truly capable generalist models more efficiently.
Now, it's important to note the paper does acknowledge some limitations. It's English only for now. It doesn't explicitly verify post-training improvements like fine-tuning, and highlights potential data constraints if you filter too aggressively with a small starting pool. It also focuses on hard filtering keep or discard versus maybe more nuanced data weighting. Plus, that fast text performance anomaly, that still remains unexplained, which is just, begging for more research.
Absolutely. So thinking about the bigger picture, this deep dive suggests that progress in language modeling isn't just about finding better data selection methods, though that's clearly important. It's also about having profound clarity on what capabilities we truly want our models to have in the first place, and crucially, how we effectively measure that progress. The benchmarks we choose really matter. So maybe the final provocative thought for you, our listeners, is this. What stands out to you about how this research might change how we evaluate and ultimately how we build the next generation of LLMs?